So welcome back. And what we thought of doing today is to have a more extended lecture because we skipped last week and then we focused more on the lab. And the reason why I wanted also to do this is that the gradient methods and the energy optimization is going to be an important part of what we end up doing. And I will try to motivate why. Now, I decided also to skip a little bit this discussion about the Fokker-Planck equation and the Langevin equation, because there are many technicalities which many of you are not too familiar with from transport theory and statistical mechanics. However, if you go to the weekly material which we have, and you take a closer look at the material which you have access to. So if you go into the doc folder and look at the published material and go to week 4, and that's where we discussed the week 5 was last week. If you go in here, you will find return to, I didn't like that one. Okay, let's try again. So in week 4, and if you go to the PDF section here, you will find the slides about the diffusion equation, especially those slides. And take a look at those because they contain the derivation of the Fokker-Planck equation. They start with basic elements from the master equation and transport theory, which probably not all of you are familiar with. For us, this serves more as a background material so that you see the link between the Fokker-Planck equation and the Langevin equation, which we implement. So you can take a top-down view on it and just use those equations which we discussed, which you have to implement. And because if we are going to go through that, that will quickly be some, at least some 2 hours of lectures, and some of the things are very technical. So take a look at it and use it as a background and for self-study. And if you want to study more about transport theory, that is a big topic by itself. But I did place a lot of material there, so you can study it. And if you have questions, please come back. Now, the thing which I wanted to say more about now is a topic for today, which becomes very important for us. And this is essentially about optimization and derivations of the equations for the gradients of the energy. We are going to look at gradient methods, and you have already encountered many of these methods before. So I know that both of you have taken courses in machine learning. So you have seen Newton's method. And then from Newton's method, one of the things you probably remember is that Newton's method is actually you truncating around a point and keeping terms in the Taylor expansion up to the second derivative. Now, if you have just one parameter, then the second derivative is something which we could calculate. What you're going to see here is that the second derivative is going to lead to 7, 8 integrals we have to evaluate. So we're not going to do it. We are going to evaluate the gradient. That means that since you don't want to evaluate the second derivative in the Taylor expansion, which leads to Newton's method, we end up with what is called quasi or semi-Newton methods, like Broyden's algorithm, standard steepest descent, etc., etc. So we're going to discuss them. But the first thing I want to do now is to bring up the overarching thing. Why do we do this? So let's take a look at what you guys have been getting when you've been running your codes. So let's just go back to the whiteboard and stay a little bit within the whiteboard context. So what we have done is to calculate, and exactly this is what we are doing. So we are calculating the expectation value of the energy as a function of a set of variational parameters. And in our case, we are evaluating this integral. So let me just rewrite it in full glory. And then we have a Hamiltonian, which depends on the positions of particles. It can also depend on additional quantum numbers like spin, etc. In our case, we have a spinless Hamiltonian. So I'm just going to set up here the calculations, and this is multiplied with a volume integral and divided by the norm. So this is the quantity which we have been evaluating till now. And if we now just stick with one parameter, so what we calculate is the expectation value of the local energy. So this integral which we are evaluating is actually given by the probability, which we have defined before, P of alpha, multiplied with this local energy, which depends on the positions and alpha, and then d of r. And then when we do the calculations, the way we have done things now is what we normally would call the really brute force way. So we have then evaluated the integrals as a function of these parameters alpha. And now what I'm going to say is that alpha, instead of a vector, is just given by one variable alpha. And then we have alpha here. And then what we've seen then is something like this as a function of alpha. And there is an alpha optimal here, which we indicate by the hat. This is the expectation value of the local energy. And we just write it like this. And typically what we have done then is to just set up a whole set of parameters. So we have an alpha 0, we start with an alpha 1, and then an alpha 2, and this just goes on, and then we've moved on here, some alpha n plus 1, etc. And in every case here we have a value, and then we make a final plot, and then we can use this data to find this minimum here. This is essentially what we have been doing till now, and this is what we would call the typical brute force approach. So you calculate, and then you plot, and then you try to use this data set and find some interpolation scheme which allows you to find the minimum. Now, in each case here, we would typically run this, suppose with the number of Monte Carlo cycles, MC, this could be 10 to the 8, just to give you an example, if you want good results. You would do the same here, you would do the same here, etc., etc. So this is a quite expensive calculation. Now, the question is now, can we do something smarter? And this smarter is actually related to the optimization part. So the whole thing which we are going to do now is to start with a guess for alpha 0 or for alpha. So we would then start with a guess. And one of the things which you have seen is that if the interaction is weak, like in your case now, it's going to be pretty weak for this system of bosons. Then what you could do if the interaction is weak, and since you have a product of single particle wave functions, what you could think of then is that a good guess would be something around the minimum for the non-interacting case. The non-interacting case is something which you have been exploring. I hope everybody has done that and have a code which does it. But then what you've been doing is simply to run this in a very, very brute force way and calculate these expectation values with tons of Monte Carlo cycles. So the kind of idea now is rather to start with a guess, and let's just call this an alpha 0 prime, like this. And this could be something which places us here. So this is our guess. Could be a random guess, but normally it's a guess which is guided by our insight about the physics. Now, what you could do then, instead of having 10 to the 8 Monte Carlo cycles, we could get away with something like 10 to the 4. And then we evaluate the gradients. So we calculate the gradient of the energy. So we would calculate a delta alpha of the expectation value of the energy. And then with that gradient, we are going to step ourselves towards this minimum till the gradient is 0. And this is essentially the way we are going to implement Newton's method. So what I'm going to do now, I hope you don't get offended, is to remind you about Newton's method. Then the other thing which we need to do is actually to calculate the gradient. So this gradient is going to be given by three integrals, which we have to encode. The whole thing then is that when you have these gradients and you found this optimal value, that is when you will start the big Monte Carlo machinery. So you found the optimal alpha, and that is where you then mount your main calculation. And then you will typically run with millions and millions of Monte Carlo cycles. Does that sound like clear agenda? So what we need to do now is just to fill in the details. And this is essentially what today's lecture is about, and the kind of methods which you will encounter. And typically for this case here, where we have very few variables, what we would end up doing then is to use one of these popular quasi-Newton methods, which give an estimate of the second derivative. So one of these methods is called Broyden. Another one is called Powell, which you probably have encountered because these are options when you use scientific Python, the optimization part. You will call these methods. So these are all methods which try to approximate the second derivative in Newton's method. Now, I've been talking about Newton's method. Let me remind you of that now, so that we have many of you have seen this when you took a course on machine learning. So let's do a quick reminder here. So Newton's method first. And we are going to make life a little bit simple. It's actually called Newton-Raphson's method. According to legend, Raphson was Newton's assistant, the same as an associate professor, and was the one who actually ran the business. And it was Raphson who, according to legend, developed the method. So I'm going to introduce some kind of shorthands now. So the expectation value of the local energy is something I'm going to use a shorthand for. I'm just going to call this for E of alpha, just as a shorthand. And then we are going to let alpha, instead of being a vector, we are just going to look at a scalar. So in our case, in project one, we actually have only one parameter. So this is justified according to the project. And then we know that if we just stay general and look at the gradient in terms of these parameters alpha, which then would be, if we now look at a general case, this would then be given by the gradient. I'm just going to write it like this. But in our case, this G, this gradient of alpha, is just going to be a function of one variable. Okay? And what we want is obviously the alpha optimal, which is going to be given by this parameter alpha. So what we do now is that we prepare for a Taylor expansion. So we're going to make a Taylor expansion around the minimum, where we have this optimal value. So what we do then, if we now prepare for the Taylor expansion, so Newton's method is nothing but you truncating the Taylor expansion at the level of the second derivative. That's it. Prepare for Taylor expansion. So what we are going to have then is that we are going to expand around an alpha. And what I'm going to do now, if you look at this alpha optimal, this is this hatted quantity, minus some alpha n. And n stands for an iteration n. So we've been doing lots of iterations. If you go back to this image here, you see that we would start with an alpha 0, and then we calculate the gradients, and then we slowly move towards this minimum here. So that means that this alpha n is the result after n iterations. So that means for us now that when we are going to look at the gradients, I'm going to replace some of these quantities. So I'm going to have a G of alpha, which now is evaluated at a variable alpha n. And this is the same as D of the expectation value of the energy, the local energy. and I have skipped the subscript L as a function of alpha of d alpha at the value alpha is equal to alpha n. So these are just definitions. The other thing is that if I look at the second derivative of E of alpha, this is something which I'm going to just label as a quantity which is calculated at iteration n. And I'm going to simply label this as a quantity A of n. So that's the second derivative. So these are just notations which I'm introducing them. So if I Taylor expand around the minimum, so ideally what we are looking after are the roots of the gradients. So we Taylor expand around this variable alpha hat. So what we get then is an E of alpha hat. And then I obviously have an E of alpha n. This is next first value. And then I have plus, and then I have an alpha hat minus alpha n multiplied with this gradient. So I'm actually going to write this gradient as a g of n. So this is multiplied with the g of n. And since we are not dealing with more than one variable, we don't need to put a vector sign here. And then obviously that means that we get the next function, which has to be 1/2. And then I have the second derivative, which is A of n. And then I have alpha hat minus alpha n squared, and then plus higher order terms. So then I would have an alpha hat minus alpha n to the power of 3. So these are the higher order terms, which are then linked with the third derivatives and higher derivatives. As I said, I hope you guys don't get offended if I remind you of these things. So, but it's useful to see them and for the sake of completeness. Now, what I'm also going to do now is to introduce another shorthand where I just label this as a B of n. Just this difference for the sake of simplicity. So that means that my equation then is something which is going to look like an E of alpha hat, which is equal to this E of n plus this G of n multiplied with B of n plus 1/2 times A of n multiplied with B of n squared plus higher order terms, where now I have B of n to the power of 3 or higher. This is the scalar expression. If I treat these as vectors now, I'm just setting up the more general formula for that. Then what we would have is that this E of alpha is then given by this E of n. But then I have to be a little bit more careful now, because then the gradient becomes a vector. So I need to put this one like that. And then I have a B of n hat here. Now, this alpha is also a vector, the alpha hat, but I'm not putting an arrow on it, simply because it becomes a little bit, I would say, untidy, the equation. So then I have plus 1/2, and then I would have this B of n vector transpose times the matrix. This becomes a matrix, and this matrix is the Jacobian. This is the second derivative of B of n as a vector again, and then we have this higher order terms of B of n to the power of 3 or higher. So when we, for those of you who took a course in machine learning, you may remember that this is actually what we did when we derived Newton's method to do the optimization. Now, what we do next is that we would typically truncate, but let me give you an example here now. So suppose now that instead of this being just a scalar, like in this case, suppose now that the alpha is now a vector and it's given by two components. So I would have an alpha 0. It could be in the beginning, we start with an alpha 0 and alpha 1. And then we are going now to put in, so these are the two parameters we want to find. And then I have an alpha n then, which then would be given by some alpha 0 at iteration n, and then an alpha 1 at iteration n. Now I have two parameters in my function, which I want to optimize. So that means that this quantity an is actually a matrix. And you have encountered this before. So this matrix then is then given by the second derivative of the energy with respect to alpha 0 squared. And this is then evaluated at alpha equal alpha n. So in this specific case, this is alpha 0 equal, let me just put the correct indices. So this will be alpha 0 at the nth iteration. Then we would have the next term, which would be a d second derivative of d alpha 0, d alpha 1. And this will be evaluated at the two values, alpha 0 at iteration n and alpha 1 at iteration n. So what I'm saying now here, just for saving notation here, I'm just putting alpha equal to alpha of n. So when I say that, it means that this one contains both alpha 0 and alpha 1. And you're probably familiar with this object because this is just the Jacobian. And then we will have a d alpha 1 of d alpha 0. And then we would have a similar one here of alpha equal to alpha n. And finally, we would have the d of e of d of alpha 1 like this. Now, the problem which we are going to face when we do the Monte Carlo calculations is that the gradient itself is already a complicated expression given by three integrals, which we have to evaluate by Monte Carlo calculations. This quantity here is going to be given by 7 integrals, which we have to evaluate by Monte Carlo integration. And if you think that you're doing 10 to the 4th, 10 to the 5 Monte Carlo cycle for each iteration here, this becomes expensive, even for 2 parameters. And also, since it's going to be the sum with pluses and minuses of different integrals, we can have accidental cancellations of large numbers. So the numerically inaccuracy is going to be high for this calculation. And that's normally why we don't do it. Now, if you look at Newton's method, it means that Newton's method, we simply neglect higher derivatives. So we neglect the terms which go like this parameter b of n to the power of 3. So that means that our optimal value is going to be given by alpha hat, which is e of n plus, and now we have, and I'm keeping this as vectors now in a sense. So this is going to be given by this b of n plus 1/2 of b of n transpose multiplied with the matrix multiplied with the vector b of n, which is just the difference between the iterations here. So what this looks like is actually a function which many of you probably have seen before, where we have some constant c plus a vector g, which is a gradient, times x plus 1/2 x transpose times a times x, where a is not necessarily the same as the matrix. This is something which you probably have seen before in different courses. And essentially what we are doing with Newton's method is to optimize this problem here. We are going to find the roots of this function. So we want to have where f of x is equal to 0. Essentially, that's what we want. So if you think of this function here, if you just look at it, if you now look at d of f of x equal to 0, that means simply then, when I take the derivatives, that this, since c is a constant, what I get is a times x plus g. This is a quantity we want to find the roots of, right? And this is you would get the same equation if these x's and g's are scalars, or if they are matrices. So you have a second order expression for the function. This is essentially what we have done here. And this is actually the basis function for this kind of optimization methods. In our case, this function arises from a Taylor expansion around the optimal value. So if we then plug this in, put this one equal to 0, then we see that x is equal to A inverse times G. Like that. Now, if you can think of a simple example, so let's just take a simple example here to quickly remind you of some of these technicalities. So here's a function of two variables, x1 and x2. And we can write this one as a function of these two variables, x1, x2, plus 10 x2 squared. This is just an example I cooked up. Then we have a vector x, which is given by two components, x1 and x2. These are the two components. And that means that I can now rewrite this equation here in terms of a matrix times these vectors. So I can rewrite this function x1, x2 here in terms of 1/2 times this vector transposed times a matrix, which is now given by 2, 1, 1, and 20. And you can see when you write this out, you will actually get back this equation. And this would then be given by a vector which plays the role of the gradient of x1, x2. If you do the algebra here, you will then find that when you multiply out these vectors with the matrix, and in this case, 5 and 3 plays the same role as we had for the gradient. So if you look back at the example here, then this vector which we put in there, which is just written as 5 and 3, this plays in a certain sense the role of the vector, or the gradient, sorry. Then the optimization part here for us is simply given by d of f of dx1 equal to 0. That's one of the equations we want. And that gives us simply, when we set up the equation, 2x1 plus x2 minus 5. And then we have the next one, which is df dx2 equal to 0. And that gives us x1 plus 20 x2 minus 3. And then you can start with a guess for the iteration. One thing you should note, and this is just a mathematical small digression, is that this matrix is actually positive definite. And if the matrix is positive definite, then there's a theorem for these kind of iterative processes that it will always, irrespective of starting point, it will converge to the exact value. So in this particular case, you could start the guess for iteration. Now, this is a waste of time because we can solve these two equations. So by just doing substitution here, you find an expression for x1, which you feed in here again, and then you have the solution. But you could solve this iteratively. So you could guess for iteration. You could then start with an x0, the first guess, where you simply just put in some values, -3 and 1. Just this could be random values. And then you would start the iteration. So what we need now is actually the following. So what we need in our case, so if we now go back to our specific case, what we need is the gradient, del alpha, of the energy as a function of alpha at this optimal value. And this alpha optimal is going to be given by alpha after n+1 iterations. So we are hoping that after n+1 iterations, we have reached the holy grail, the point which we are looking after. So what we want then is the following. So we want that this del alpha, this quantity here, evaluated at the optimal value, which is now replaced instead of alpha hat, we have alpha plus 1 here, n+1. We want this one to be 0. And in our case, this is simply given by g of n, when we take the derivative plus this matrix evaluated at n times this vector b of n. This is essentially what we want to have. And in our case, this quantity here is just the alpha, the gradient of E evaluated at alpha n, different values. And just let me quickly remind you, this b of n vector is actually given by alpha n plus 1 minus alpha n. And this leads to the solution of this leads to the famous iterative method, which you have encountered many, many times. Because if we now plug in this value, if we plug this in to this expression, which you have, this one, we plug it in here. No, sorry, in from this b of n, we plug it in here. Then we can isolate the terms. And what we get then is that if we look at this equation here, this gives us simply the standard iterative method, which characterizes Newton's method. So we would have minus, and then we have an inverse multiplied with a gradient g of n. In our case, we don't need to deal with a gradient because we simply have it. And then we just reorder. So we have alpha n plus 1 is equal to alpha n minus, and now we should be a little bit careful because we should put vectors on this. Minus this matrix times the gradient here. And this is something we can frame in. This is nothing but Newton's iterative method, or Newton-Raphson's iterative process. Newton-Raphson's iteration. Son's iterative method. And this is something you've seen many, many times. And typically what we would do then is to iterate this till the difference between alpha n plus 1 and alpha n is smaller than a fixed constant, which you have set. And you know that the root of all evil is actually buried into this function here, which even for this petite case of two variables is given by this matrix, which we then would have to evaluate and invert for every iteration, because for every iteration, we have new values of alpha n. So if you go back then, what we are going to have then is that we solve this iteratively. So solve iteratively. Starting with a given guess, alpha 0, and repeat to that, and repeat till the difference, the norm 2 of alpha n plus 1, not hat, but a vector, minus alpha n, and norm 2 here is smaller than some prefixed quantity. And this quantity could be something like, let's say, 10 to the minus 5 or other values, which you set. Yeah. This is a norm 2. So the norm 2 of a vector, let me just remind you of that. So the norm 2 of a vector, if we take a vector x, this is nothing but the sum over all the components of a vector of x of I squared and square root. No, sorry, it's actually not like this. I was a little bit too fast here. It's actually this quantity. If you then write it like x squared, x norm 2, so this is a norm 2. The norm 1, I'm just going to put this up for you. This would then just be the same as I equal 1, and this is what you would call the inner product of a vector. If you take the norm 1, so these are just some standard definitions, The norm 1 of a vector is just you taking the sum from I equal 1 up to n of the absolute values of the elements. That's norm 1. And then you have several such norms. If you have norm p, that means simply that you have xi to the power of p. So these are just different popular norms which are used, and it's a more compact way of writing a specific expression. So in your case, what you would do then, since these are vectors, you would simply take the inner product of that vector and then take the square root of it, and that gives a norm 2. And if this one is smaller than a specific quantity, then you would stop the iterative process. And this is basically the gradient descent method, which many of you have encountered already. Now, the problem, and if you go back to a course in machine learning where optimization plays a central role, it's actually at the heart of all machine learning methods, then we know that we want to evaluate, and you will see now later today, when you look at the integrals, these integrals for evaluating the second derivative, you don't want to encode them because you're going to get 7, 8 integrals which have to be evaluated, and that is going to steal a lot of CPU cycles. So we want to avoid to evaluate this A of n, and what is pretty common then is to replace A of n, the second derivative, with a constant. And this is normally called, in the literature, is called the learning rate. You're familiar with that, right? So that means that the actual recipe, which we end up implementing, of an plus 1, like this one, is given by the previous value minus gamma of n. And then it depends on how you update this learning rate. So you can update it per iteration with some information about the gradients. And that leads to a whole hierarchy of optimization methods. Or you can just replace it by a constant. If you replace it by a constant, which you keep fixed throughout all the calculations, this leads to the standard plain gradient descent. So I'm going to set this up just to remind you quickly about some of these methods. So essentially what we have is this recipe here, which you will typically write in a more compact way, like alpha being updated with an alpha minus some gamma times the gradient. This is the kind of more compact notation which you will often see. So if gamma of n is not updated iteratively, then we have a constant equal to a constant throughout the calculations. And that leads to the simplest possible approach, which is just the plain gradient descent. And you have encountered these methods before. Okay. Any questions so far? The matrix A is? Yeah, we are. That's a basic assumption because we are going to deal with Hermitian quantities. So it's going to be symmetric or Hermitian actually. Now, one thing you can do, if you want to see, and let's do that before we take a break. So one thing we could do now, if you look at the expressions which we had, you can ask yourself how to find an optimal gamma. So can we find, and this leads us to the first method, which is called steepest descent. Have you heard of that? So how can we find an optimal gamma n? So what we could do now is to make another expansion. So what we are saying now, since we know that this alpha hat is equal to alpha n plus 1, and this is equal to alpha n minus gamma n times g of n. What we do now is simply to expand, perform a Taylor expansion around this one. And that's going to give us a nice expression. So what we do then is that we expand the energy. So we take the energy and we simply expand this around alpha n minus gamma n times g of n. And if I do that, this is simply going to be given by E of n, which is E evaluated for this specific value. And then we have minus, we get gamma n, and then we have g of n, the gradient, times the gradient again. I'm just doing a new Taylor expansion. And then what I get is plus 1/2, and then I have gamma n squared. I have my gradient evaluated at the point n, multiply with the second derivative. And what we do now, we keep only terms to second order, to the second derivative. So we are going to put an approximation sign here. We leave out the higher order terms. And then what we do then is simply to calculate the derivative of the energy with respect to gamma. So what we do then, we simply say, okay, let's take the derivative of the energy with respect to gamma n, and we want that to be 0. We want to find the optimal value. This is, again, another optimization value. If we do that, we can find a value for gamma n, which is given by g of n vector times t times g of n. It's pretty easy to see that from the algebra. And then we have a g of n transposed, multiplied with the matrix times g of n. Keep in mind now that this is a matrix, which is the second derivative, with the second derivative of E. This is the Jacobian. Now, this is a very nice formula, but for us, it's not very efficient because we have to evaluate the second derivative. So it's a way to find an optimal gamma. And actually, this method here has this recipe, which you see here, is nothing but a standard method in optimization theory, which is called the steepest descent. Now, there is a whole hierarchy of such methods. Probably some of you have taken a course in optimization. I don't know if you've done that. And then you've encountered something which is called the conjugate gradient descent. All these methods require that you're able to evaluate the second derivative and able to evaluate that matrix. So we don't want to evaluate that. And that leads to a whole set of methods we don't want to evaluate. And I will show you after the break why you don't want to do that, because the expressions are not going to be nice. So we don't want to evaluate A of n. So that's going to lead to a set of methods. So one, the method which are called quasi-Newton methods or semi-Newton methods. Newton. And they contain methods like Broyden's method. So Broyden's method is actually a very simple method where it uses the second rule to evaluate the second derivative. Then there are modifications of that, and one of these is very popular. It's called Broyden, Fletcher, and then there are two more guys, which I always forget the name of. Fletcher, and I think it's Goldberg. I always miss it, and then Farberg. This is a method which is an improvement of Broyden's method. And you will often see that shortened to an acronym like BFGF. And if you use SciPy optimize, you will see that the BFGF is an option which you can plug in. No, wait, it's not Farberg, it's Shannon. I'm sorry, I mean, I always forget these names. It's Shannon or Shannon. I don't remember exactly, so it's BFGS. Then you have other methods like Powell's method. And this continues. Now, these methods are useful if you have few parameters. So if you run a traditional variational Monte Carlo calculation, you have often something like 5 to 20 parameters. And then these methods are normally the chosen ones. However, if you wish to use neural networks to optimize a wave function, which would be a topic for the second project, then with neural networks, this method here would not be very efficient. And then you would come into the domain of methods like the gradient descent GED plus momentum. You would have stochastic gradient descent with and without momentum. You would have the Adams optimizer, which many of you have encountered. You have ADA-grad, root mean square propagation, RMS plot, etc. So these methods are when alpha n, this vector, is large. So that it has a large dimensionality. So typically this vector here is an element of real numbers to a power of p. And if p is large, then you would typically opt for these methods. In our case, in project 1, the methods of choice would typically be one of these methods here. And you will see that in the examples. But now we need a small break. And the thing which is interesting for us now is actually the calculation. And this is where we start after the break. The gradient itself of the expectation value of the energy. Sorry. And this is the quantity which we will derive after the break. And this is going to be given by 3 integrals, which we will have to evaluate. Yeah.
Because we want to obtain a gamma constant.
Yeah.
To use that instead of the A.
Yeah.
But then the gamma n depends on A itself.
So if you look at this case here, so what we did now, the general expression is this one. So what we have then is a gamma which we ideally would like to reflect some information about the second derivative. That is the ideal. So then you're looking after a recipe which allows you to update this iteratively. Now, the brute force way is simply to say that this is a constant throughout the calculation. So like when you did a plane gradient descent in a neural network calculation, you simply set up an array of values of gamma, like 10 to the minus 5, 10 to the minus 4, and so on. And you did the calculation because that was numerically less expensive than calculating the second derivative. Then what you did was that you picked the result which gave you the best, let's say, cost function. And then you were happy. So this is what we call the brute force approach, the simplest possible one. And that's what I have implemented in the program here. So in the program, in the lecture notes this week, there's one case where I just do plane gradient descent, but then you have to tune the learning rate. Another thing you can do is actually to update the learning rate iteratively. And one of these methods is steepest descent, which is actually based on you making a Taylor expansion with this one, where gamma n is now updated at every step. Now, in case you can calculate this matrix efficiently, then you can use this formula here. And that gives the method which is called steepest descent. But you would only do that in case you can evaluate the vectors and the matrices in an efficient way. In some cases, if you were to use, let's say, standard linear regression, then that matrix is replaced by your feature matrix, if you remember from the machine learning course. And that's something which is fixed at the beginning. So you can actually evaluate that matrix from the beginning, and it doesn't change. However, when you now do the iterations, this matrix depends on the second derivatives, which change for every value of n. So that means that this recipe is very useful if A the matrix stays constant for every iteration. It doesn't change. And there are differential equations. If you go back to this example, which you see here, this simple example, which I put up, this one. This is an example where the matrix is the same. For that case, I could have used the steepest descent. And you will see that that's going to be better than the plane gradient descent. But this matrix doesn't change. Our problem is that it changes because the derivatives change. So what typically happens in our case is that if we have few parameters alpha, we would use one of these methods, and you will see that in the calculations here. If we have many parameters, if we are using a neural network, for instance, then we would typically go into stochastic gradient descent with Adams, Adagrad, or these other methods to update the learning rate. So the whole thing is that you want to find a way to update this learning rate. Did that help? Okay, let's take a small break, yeah? So what we need to look at now is the calculation of the gradient, because we have now opted for Newton's method, and the method we are going to implement in its simplest form is what is normally called the plane gradient descent. But we can obviously refine that, but this is the quantity which we're going to look at, and we're going to replace this one with just a parameter, which we call the learning rate, but we need this one. So let's look at the derivation of the gradient of the expectation value of the energy as a function of the parameters. So let's now simplify some of the equations a little bit. So I'm going to simply just remind you quickly about the local energy, and I'm going to be a little bit sloppy with vectors and so on. Hopefully it comes from the context what we are doing. So what we have defined is the local energy as a function of x. Now I just write x, a generic variable. We don't need to specify. And then this is a function of the parameters alpha. And we know that this one is given by the trial wave function of alpha of x and alpha, multiply with a Hamiltonian, which depends only on x, and multiply with the psi of t of x alpha. Now I'm going to make life a little bit easier for myself now. So I'm not going to have this t trial. So I'm going to simplify things a little bit so that we have a less notational clutter when we are setting up the equation. So I'm going to let this be given by a alpha like this and just x. But okay, just to simplify. And we know that we have the probability of alpha of x, which is simply given by alpha of x squared divided by the normalization constant as a function of alpha. And we know that this normalization constant alpha is nothing but the integral over d of x, and then we have psi of alpha of x squared. And this is something which we also, if we look at this probability distribution, we know that if we integrate d of x, p alpha of x, this is normalized to 1. And what we are calculating is the following quantity. That is the expectation value of this local energy. So I'm going to let the local energy, this EL of alpha, as we wrote it before, I'm just going to write it in terms of the expectation value, just E of alpha, like this. Again, to simplify. You can think of this as just one parameter, or it could be a vector. And then from the context, you would decide which are the relevant quantities. So this is basically the quantity which we are calculating. And we have x of alpha here, like this. And this is the expectation value of the local energy. And this is what you have been implementing. So what we need now is to calculate derivatives. And let's do that. So our quantity, when we look at it, so what we would do now is to start from the basic equation. So we have E of alpha, this expectation value, which is just now the integral of d of x, and then we have psi of alpha, complex conjugate of x, and then we have h multiplied with psi of alpha of x, and divided by the norm here. So what we could do now is that we could assume that the alphas are real. There is no complication, but it's a complex case is similar. You just need to take into account the conjugation. Okay, so just for simplicity in the calculations now, and in your case as well, if you look at the harmonic oscillator wave functions, they're actually real if we don't take any angle dependence into account. So assume now that this psi of alpha is real. So the complex case is just similar with conjugation. And then I'm just going to define some quantities here, okay? So I'm going to define a quantity which I call for A of alpha. This is just to simplify the calculations a little bit. So I have phi of alpha, h. I'm assuming that the psi is now real, but there's no problem in just setting up the same function with a complex quantity. You just need to take into account the conjugation as well. So then we know that if we're now calculating the derivative, so what we have then is that the energy which we have is actually equal by given by A divided by B. So that means that d alpha of the energy obviously has to be given by d alpha of A multiplied with B minus A of d alpha times B divided by B squared. I guess that doesn't come as a surprise. So if I then look at the different terms which we have to deal with, you know that d alpha of B is simply equal to d alpha of this integral dx of psi alpha squared. So that has to be equal to d of x. And then I have 2 times psi of alpha multiplied with d alpha of psi alpha. So just keep in mind now that when I write this d alpha, this is the same as d alpha, okay? Can you see properly? Yeah, this is the denominator, right? The denominator has the wave function squared. And I'm just assuming now that the wave function is real. So then I just have in the denominator squared quantity. This one? Yeah. No, because it's with respect to alpha. So, yeah. So it's only with respect to the variable alpha. And then if we now look at the numerator, we have to take the derivative of d alpha of A. And that is simply, when we do the math here, this is a d of x. Then what I get is a d alpha of psi alpha multiplied with h times psi alpha plus psi alpha multiplied with h. So h does not depend on, the Hamiltonian does not depend on the parameters. And then we have a d alpha psi of alpha, like this. Now, if you can assume now suitable boundary conditions. So the typical boundary conditions is that the wave function disappears when x goes to plus and minus infinity. That's a pretty common one. And then we also keep in mind that the h is Hermitian. And that means that if I look at this integral which you have here, and you've probably gone through these kind of calculations when you took a course in quantum mechanics, then what we have is a d of alpha psi alpha. Then this quantity is actually equal to d of x of d alpha of psi alpha times h times psi alpha. And that means that this quantity d of alpha of A is actually equal to 2 times d of x. And then I can write it like d of alpha, psi of alpha, times h acting on psi of alpha. Then if we do the bookkeeping, so this is just a matter of bookkeeping. Again, it shouldn't come as a surprise that the formula for the first derivative. So if I now insert these equations, what I would get then, when I insert everything, then what I have is that d alpha of E, and what I'm using now is that A is actually equal to the energy multiplied with B. Pretty straightforward to see that, because the energy, so we can then replace the equation with a 2, and then we have a integral d of x of d alpha, psi of alpha, h times psi of alpha. So let me do this properly. So this is multiplied with b, and then we have minus, and then we have e times b, which is a, and this is then multiplied with the derivatives of b, which is d of x 2 times psi alpha times d alpha of psi alpha, like this. And this has to be divided by the denominator, which is b squared. And you see now that there is a b which disappears, one here, and one here, and also one here. So when we then set everything up, what we get is that this expression looks like as follows. So we would then have an integral over d of x, and then we have d alpha, psi alpha, and then we have h psi alpha, like that, divided by the norm. So d of x psi of alpha squared minus, and then we have the energy here. This is the local energy. And then we have a d of x. Actually, this is the expectation value of the energy. So this is E of L. And then I have psi of alpha. And let me see if I can sneak it in here. So because here I should have a multiplication with d alpha, psi alpha. And this term is also divided by d of x. Sorry for this little bit ugly way of setting it up. Now, if you look carefully at this, you see now that these are 3 different expectation values. So this quantity which you see here, so we have the wave function. If I now multiply with the wave function and divide by the wave function here, this is nothing but the local energy. And then I have the wave for this quantity here, and then divided by that one. And that is the same as a probability, which we can sneak in here. So what we are going to get then is something when we now bring everything together. So let me just do this intermediate step here. So divide and multiply by psi of alpha. So what I'm going to get then, if you look more carefully at this equation, so the first term, which is a d of x, and then I have a d alpha of psi alpha multiplied with h of psi alpha divided by the norm here, d of x of psi alpha. This quantity here is nothing but d of x, and then I have psi alpha squared, and then I have the derivative of d alpha psi alpha divided by psi alpha multiplied with h times psi alpha divided by psi alpha. This quantity which you see here is nothing but the local energy. This quantity which you see here, this one divided, so I actually forgot to take the expectation values because we have a psi alpha squared of d of x. So what you see now, if you think of it, this is a probability. This is the local energy. And this quantity here is something which we can write in a more compact way. So is there a quantity, a mathematical function, which we could use to rewrite this expression here? Does it ring a bell? You say,
This is the local one?
yeah, exactly. So if you look at this term here, this one, this is nothing but d alpha of ln psi of alpha. This is the local energy. So I can actually rewrite this term, which you see here, as, so let's just do that. So this is nothing but the probability which we have defined, P of alpha of x. And then we have d alpha ln psi of alpha multiplied with the local energy times d of x. And this is the expectation value. If we just write it like this is the expectation value of d alpha ln psi of alpha multiplied with E of L. Then, so that's one term. Let's now look at the the other term which we have here. I mean, we have this term as well. So if you look at this term, what you see here is the expectation value of the energy. If you then look at this term, if I now multiply in here with psi alpha and divide by psi alpha, I'm going to get a probability multiplied with the log, the derivative of the log. So when I collect everything, so collecting, if I do that, then what I have is that d alpha of the energy, the expectation value of the energy is going to be equal to 2 times. And now I have this expectation value of d alpha ln of alpha, no, psi alpha, sorry. Psi alpha multiplied with the local energy, which depends on alpha, like this. So this is one expectation value, minus the expectation value of the energy, the local energy with respect to alpha, and multiplied with the expectation value of d alpha of ln psi alpha. This is my gradient. That's the quantity I now need to encode in order to be able to perform this type of calculations. So what we end up with is to have to evaluate two such quantities. There is another interesting aspect here. If we now simply rewrite, suppose we rewrite this quantity d alpha ln psi alpha of x, which is just equal to d of alpha psi alpha of x divided by psi of alpha of x. This is something which I can now just replace with an operator O of alpha of x. So that means that what I'm going to calculate then is a d of alpha of E, the expectation value of the energy. Remember that this is the same as the expectation value of EL alpha. And this is going to be equal to 2 times, and then I have this operator, the expectation value of this operator alpha, multiplied with the local energy, minus the expectation value of this operator, which I have defined, multiplied with E of L, like that. Now, this is an interesting expression. So if you're taking a course in statistics, this is something which we can write in a more compact way. There is a famous quantity in statistics. So we have the mean value, we have the variance, but then there's another quantity beyond that. Yeah, but you have another quantity which you would calculate. So if I were to replace this one with the local energy, it would be the local energy squared minus the expectation value squared. That's the variance. If I have two different quantities, this is the covariance. So what you have here is actually the covariance. So this is 2 times the covariance of this operator alpha and the local energy which we have here. But you see now that this is what we need to evaluate. These integrals which you see here, they are going to introduce an additional error, because we are going to take the difference between two numbers, and that can easily lead, if you don't have many Monte Carlo cycles, to problems. But we are going to see that in the examples now and how we are going to perform the calculations. So this is roughly the calculations which we need to deal with. So there's one thing I wanted to actually add here, and that is why we don't calculate the second derivative. So in the slides you will find, so let me just bring that up so we can take a look at it. And this is more for the sake of completeness. So let me just see where I have those slides. I just need to bring it up. So I put in some additional material here. So the quantities which you have seen is this slides within the material is actually covered here. And let me just bring that, share that one so that it comes on the recording. So the first part here is essentially what you saw first. But now we are going to look at the second derivative, and that is the Hessian. So let's now take a full screen. So when we are now looking at the equations, what we did till now, this is essentially what we have done. And if you have a complex case, then you would quickly see that this is the way you would have to rewrite the equation. It's not that difficult. But then, when we now are dealing with these quantities, we would now like to ask what is the second derivative. And if we are now doing that, we would have to take this quantity here, which now has this, which is actually ending up with this expression here, where beta can be equal to alpha. So we need then also the derivative of the energy with respect to the two parameters. So when you collect all these expressions, you would end up with a second derivative, which now contains all these integrals to be evaluated. So this is a very compact notation, which you see here for the second derivative with respect to two parameters, alpha and beta. If it is the diagonal, this is just alpha squared, obviously. And if you do that, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Some of them can be simplified. But you see, this is the main reason why you don't want to do it. Yeah.
If you only have one parameter.
One parameter, it's actually possible. And if we now go back to the Jupyter notebook for this week, you will see that we can actually calculate, for instance, quantities like that. The thing which is also interesting is that these quantities are actually proportional to the variance. So let's look at if you just have one simple functions like you have now, then this is doable. And this is essentially what we've done in the programs, in the lecture notes. So let me swing back. You can look this up, and you can, I have added more math here actually, and how you do the Monte Carlo estimations, etc. But let's now go back to the Jupyter notebook. Let's just do that. That one. Just have to find the right notebook here. Okay, share that one. This is the one I want to share. Stop sharing. Actually, this is the one I want to. Let me just find the right notebook here. Not that one. Right now, I have too many windows. That's the one. No, it was not that one either. No, here it is. It should be this one. Now, why doesn't it come up here? Let me just do one thing here and just kill this one and then restart it again. Sorry for that. Let me just restart it. So let me get. Here we are. Now it should be. Sorry for this inconvenience. So let's now go back to Zoom and share the correct one. There we are. Okay. So in the Jupyter Notebook, which you have this week, there is actually one first case, which is essentially what you have in the project. And we know that when you calculated the local energy and the energies, etc., we have analytical answers for these quantities. And you can then calculate the derivatives in a pretty simple way when you have only one parameter. And when you have more particles, this is just something which gets multiplied with a number of particles. And then you know that you can calculate the second derivative. So here you can, if you want now, for the specific case which we have at hand, then clearly, since the wave function is that simple, we have analytical answers for the first derivative. So this is the gradient, and this is the second derivative when you have only one parameter. Especially also because our wave function, which we are playing around with now, is this one. So that means the reason why I bring this up is that this gives us a very simple way to test our program. So in the program, which you will find here, I do actually calculate these three integrals. But these three integrals is something you then can compare to the exact answers. That makes sense? So for this specific case with the harmonic oscillator, we know how to calculate these expressions. And then if you look at the condition d alpha, this one to be equal to 0, then we have alpha equal to 1, which is the parameter you've been playing around with. So I just have as a small exercise here, derive the local energy for the harmonic oscillator in one dimension, find the expectation value. In 2 dimensions, it's just an additional complication, but the expressions are not that different. And then find the optimal value and repeat the same for n particles. So it means that you have a nice benchmark. And here you can also calculate the variance analytically. Now, in general, you end up computing the expectation value of the energy in terms of some parameter sets, alpha 0 up to alpha n. And you search for a minimum in this multivariable parameter space. So what you will find in the program here is a program which now implements these integrals, which you saw. So exactly this expression here, except that then you would have a ln here, the derivative of the log. Keep in mind that that derivative of the log is very convenient. And the reason for that, so this is something to think back of. So let me just bring back this in the Jupyter, no, on the whiteboard, because I wanted to mention this for you. It's an interesting technicality. So if you look at the expression which we put up for this derivative, so we have d of alpha of psi alpha of x. divided by psi alpha. This is something which we would compactify in terms of ln of psi alpha. If you look at most of the ansatzes which we have for the trial wave function, psi of alpha in our project 1 is actually proportional if we take away the constants of e to the minus 1/2 of some parameter alpha squared times x squared. And then you see why this is convenient. Because when we take the log, we simply have minus 1/2 times alpha squared times x squared. And that makes the calculation of derivatives even simpler. This is often the type of trial wave function which you end up when you do a standard variational Monte Carlo calculation. Because then you would have a trial wave function, a total psi of alpha, and now we put in a vector sign here of some x. This can often be given by a product of a single particle quantities, where you have some e to the minus 1/2 and one of the parameters, alpha, so this doesn't have a vector sign, so we could call this alpha 0, and then I have an x of I squared. But then this is multiplied with a function here, I less than j up to n, so this is a double product. And then I have a function here where it depends on the relative distance. This function, which is called a Jastrow factor or correlation factor, is often proportional to e to the minus or plus minus, it depends on the type of interaction which you have. And then you may have some other parameter, alpha 1, multiplied with the relative distance between the particles. And you see again that when you're taking the log here, you see how interesting this property is if you have functions like this, because one, this is a product. With a log, it just turns into a sum, which makes it much easier. You have exponentials, which also simplify. This is also a double product, which you can then turn into sums. And then you have an exponential again. So this makes for this kind of expectation value, even if we have to evaluate 3 integrals now, the mathematics can actually be simplified because our trial wave function often has this kind of structure. So this was a small digression, which is useful when you're going to program your expressions. So let's go back to the Jupyter notebook. So in the program, which you will find here, is just a case with 2 electrons. And for this 2 electron case, we have a harmonic oscillator single particle piece. And then there is a so-called Jastrow factor, which we have included here. And this example here is an example where we now have a correlated piece. So these are 2 electrons interacting via Coulomb interaction. We have the local energy where we have an analytical expression for it. We have the derivative ansatz. So this is the derivative of the trial wave function as a function of the parameters. So now I have 2 parameters, alpha 0 and alpha 1. I call them alpha and beta in the program here. So these are the derivatives which I need for the wave function ansatz when I'm now plugging that in the calculation of these additional integrals. So here I'm just taking the analytical expressions, and you see now that there is a parameter here, beta, and there is a parameter alpha. These are the 2 parameters. Instead of alpha 0 and alpha 1, I just call them beta and alpha. And then I need to take the derivative of this trial wave function with respect to beta and with respect to alpha. And in this case, it's the expressions are pretty simple. So I can just return the derivative here. Then I have importance sampling. And importance sampling is as before. I calculate the quantum force. And then here comes the energy minimization part. So this is where I calculate the derivatives. So there is an energy minimization part. This program here actually also calculates the energy. So it does not only return the derivatives of the energy. So psi e, this is the derivative of the energy, which we are adding up. but it returns also the energy as expectation values, as you can see here. We are coming back to this after the break. So we take a small break now, and then we are going to go through the code here, because in this specific case, what I have done, if you look below here, this is my plain brute force, lovely gradient descent. And you see there's a learning rate, which I fix. So you have to tune that one. I calculate the gradients, etc., etc. And you can see now that after some 50 iterations, this is the energy. The exact value is 3. But you see now that the gradients are not exactly equal to 0. So I did 50 iterations. Then, and this is one of the methods we will discuss a little bit later. This is Broyden's method, which we will discuss in more detail afterwards. And this is included in the scientific Python library in the optimization package. Take a small break, okay? So what we did before the break was to develop the equation for the gradient. And this is now another way of writing it compared to those PDF files which you saw before the break. And these are the integrals which we need to evaluate. So we have this integral where we transform this one, which is a derivative of the wave function, in terms of a derivative with respect to the parameters of the log of psi. Here we have an integral with the log of the wave function and multiply with the expectation value of the local energy. So in order to optimize things now, and what we want to do is to start at an initial value alpha, and then with the gradient, try to reach the minimum as quickly as possible. And when we have reached the minimum, that is where we will start the big Monte Carlo calculation. So in the beginning, the hope is that we don't waste so many cycles on finding this minimum, and then we launch the big machinery. That's a standard recipe. If you're developing a professional Monte Carlo code, this is one of the ingredients which you need. So we have importance sampling, we need the optimization part, and then next week, when we've gone through Broyden's method and that, we are going to look at the way to do resampling of the data to get a good estimate of the standard deviation of the expectation values. So in this case, it's a 2-electron case, which we discussed some weeks ago, where we have a slightly different trial wave function. So let me just bring back the whiteboards and remind you quickly about what this trial wave function looks like. So this is a trial wave function for 2 electrons, which are trapped in a harmonic oscillator trap. So in this specific case, the lecture note example trial wave function of psi of alpha. This is actually a function which now depends on 2 parameters, alpha and beta. And it depends on the positions of the particles, x1 and x2 as vectors. And this is given by, besides a normalization constant, we just write it without that one because that disappears in the Metropolis test. So it has a -1/2 alpha squared. So this is one of the parameters. And then I have a x1 squared plus x2 squared. And then it's multiplied with a Jastrow factor. So this is the one-body part. So it's just 2 one-body wave functions multiplied with each other. And this is a solution of the harmonic oscillator problem. So if we don't have any interaction, this is actually the solution of the problem of 2 electrons or many electrons in a harmonic oscillator trap. And then this is multiplied with a term which goes like e to the power of the relative distance, xij, divided by 1 plus a parameter multiplied with xij. And this is normally called the correlated part or the Jastrow part of the wave function. Correlated or Jastrow part. And this term xij is nothing but the square root if we are in 2 dimensions, which is the case here. So it's x1 minus x2 squared plus y1 minus y2 squared. So that's the relative distance between two particles. Now, this function here is actually a function which gives a pretty good result. So the exact energy, let's just set this up here, exact energy is equal to, in this specific units, 3 atomic units. AU stands for atomic units. So if you want to convert it to electron volts, you would have to multiply with a quantity which you probably remember from the hydrogen atom case, which is 13.6 electron volts times 2. So when we have dimensionless constants over these atomic units, like in this case, then this is the exact answer when the harmonic oscillator frequency, h bar omega, is equal to 1 only. Okay, so that was just a slight digression. So let's go back to the Jupyter notebook. So what you see here is the wave function. And this is the first part is the harmonic oscillator part. And the second one is now us taking the relative distance first. And then we have the relative distance divided by 1 plus this parameter beta times the relative distance. And then the wave function is simply the positions of particles 1 and 2 in 2 dimensions. So 0 stands for particle 1, 1 for particle 2, 0 for x, and 1 for y. And then you can calculate an analytical expression for the local energy with that wave function. So the tricky part is obviously to take the derivative for the kinetic energy with respect to the correlated part, where you have a function of the relative distance. But this is doable, and this is the expression you get. And then you can take the derivative of this wave function with respect to the parameters beta and the parameter alpha. So the first derivative is just the one with respect to alpha, and the second one is the derivative with respect to that parameter. I mean, and keep in mind now that we just take the log of the function. Now, this is a quantum force. In this case, in this code, where I use a plane gradient descent, then what I'm doing is simply to include importance sampling. I do only 10,000 Monte Carlo cycles. And I calculate now set up the expressions for the energy derivatives. I have the old wave function, the quantum force old, the old position. I set up the Monte Carlo cycles. I calculate the new position. I set up the new quantum force. I perform the metropolis test here by using importance sampling. Then I update positions. I update the quantum force. I update the energy. And now you see that here, I'm going to calculate. So the delta E is the expectation value of the energy. Now, my derivatives contain now so this derivative derp C is actually the derivative answer, so the wave function. This is now the update of the derivative of C, which is this integral here, that one. And then I need to set up the local energy times this function. So you see a derivative psi and E. This is the term which, this derp psi delta E is actually the term which you now see calculated here. Local energy times the derivative of the wave function divided by the wave function. So with that, I have the ingredients which I need. And then I calculate the mean values. So my energy derivative is a mean value. It's an expectation value because I'm calculating the integrals in a stochastic way. And here you see now I have the energy divided by number of cycles, the derivative psi E, that's one of the integrals, delta psi, one of the other ones. And then I put everything together. And this returns the derivatives. Then I'm setting up the number of particles. I start with alpha. This is my guess now for the variational parameters, because I know that the alpha equal to 1 is the case when I have no interaction. So it's useful to start close to that one. So you use your previous insights. Then I'm setting up the derivatives. I just zero them here. I do the number of iterations. Then I calculate the energy and the energy derivative by calculating this function. I get the gradient for parameter alpha and the gradient for the parameter beta. And then I simply update this. So this is just a plain gradient descent, where I now have eta multiplied with the different gradients. And then I just print the values when I'm done. So I do 50 iterations. And after 50 iterations, you see that the two derivatives are not exactly equal to zero. You would like to drive them to zero. But there is a limit to how far you want to go. Now, later, when we are going to deal with the resampling methods, we are going to launch the big calculations when we found the minimum. Then we are going to start a real calculation where we do millions of Monte Carlo cycles, but for the optimal values. And you see here, my exact case without the interaction, because the interaction is weak here, is 1. This deviates a little bit, so this is alpha. And this is the other parameter. So these are the optimal parameters when I perform this optimization with 10,000 Monte Carlo cycles. Now, Broyden's method, so there's an algorithm, which is this Broyden, I have to further go, okay, BFGS. I remember always Broyden, and then I mess it up when it comes to the other three orders. So this method, however, needs you to provide it with a function which sets up the derivative, an explicit function. So that means that what I have here, if you now scroll down, these are the same things as before, derivatives, etc., quantum force. Then there is a function now which just calculates the energy derivative because it requires that. So it's a little bit more clumsy. So I still do 10,000 Monte Carlo cycles. I am setting initial guesses, which I'll feed in here. And then I calculate the derivatives using the same formula as before. So this is pretty similar. But then I have a function which also calculates the energy itself. So it wants a function which sets up the derivatives and a function which sets up the energy. So there's some multiplication. Now this is a duplication of coding here. So this sets simply up the derivatives. And here I calculate with scientific Python. I use Broyden's method, or actually it's not Broyden's method, it's Broyden FGS. And so you see now that it needs the energy. It needs also a function which is called the energy derivative. So I just did a hard brute force coding here. This method is very efficient. And this is the method which we will discuss a little bit more in detail next week, because both Broyden's method and the advanced Broyden method, the BFGS, they use the second formula to estimate the derivatives. And it's actually okay to have seen that, because these are efficient methods of typical quasi-Newton methods where you approximate the second derivative. So instead of calculating the second derivative, you are trying to approximate it. And in this specific case, we actually don't have so many gradient iterations. And you see that let me just take that one away here. And so the energy, the exact one is free. And you see the parameters are a little bit different from what we had before. Instead of 1.0 something. So this will obviously vary every time you do the calculation. So what you would typically do when you run this many times is to take an average of the parameters. But this is pretty efficient to actually set up. And you can use other types of methods if you want to. You have Powell's method. There is one which is called Kobila. There are many, many different options for scientific Python, the optimization part. But the function we are using is this minimization function here. Okay, so if you want to peep in a little bit into what is coming next week, let me just show you that quickly. Let me just go back to Zoom here. So if you go into the lecture notes here for this week, you will find a additional set of PDF files, which we are going to discuss a little bit more in detail next week. But you can anticipate it a little bit. So if you go to under the PDF folder, you will find a derivation of Broyden's method here, and the extended methods and the BFGS update. So these are normally called quasi-Newton methods, and they're actually based, no, there's a typo here. So that simply tells you that there's a human who's been writing these slides. I didn't put in the typo just by hand. This is a typo. It's supposed to be spring here. But this is something which I want to discuss in more detail next week, so that you get the background on what these methods are doing, since this is a course on computational physics. But the basic element which we start with is a gradient descent. And then this gradient descent is typically modified by these quasi-Newton methods, which allow you to circumvent the problem of calculating the second derivative of the energy. And as you saw that expression before the break about the second derivative, this is something which involves 7, 8, 10 integrals. And you simply don't want to evaluate it. But I would suggest that we stop here today, and then we look at this next week as a technicality. And then next week, we will also begin with a discussion of the resampling methods. And there is a method which we are going to discuss, which is called blocking, which many of you have never encountered before, but you have encountered something which is called the bootstrap method. That is a way to actually try to circumvent the problem of finding a proper estimate of the standard deviation. Because at the end, in these Monte Carlo calculations, what we have to provide is not only the mean value, but we have to provide a standard deviation, an error estimate of the expectation values which we calculate. Essentially because we are now calculating quantities in a stochastic way. So in a stochastic way, we can then actually estimate the error which we make using standard method from statistics. And that's what we will discuss next week as well. So the first lecture is going to be more us discussing these quasi-Newton methods, which I think it's pretty useful to have seen because you will encounter them in many, many occasions. And as we said, these methods are useful if you have few variational parameters. And also if it's easy to calculate the gradients. Okay, should we stop here? So let's do that.